Inside the chip you are using right now, billions of switches all have to agree on one thing. When miss that timing by a hair, and the whole calculation falls apart. The thing that keeps them in step is a single relentless signal. This is the anatomy of the clock. Start with a single wire. At any instant it carries just one thing, a voltage. We pick a threshold. Above it, we call the wire a 1. Below it, a 0. That is all a bit really is, a voltage that is high or low. Watch it change over time and you get a signal, a string of ones and zeros riding on one piece of metal. Everything a computer does is built on reading these levels. Now connect those wires through logic gates. A gate takes inputs and produces an output, but not instantly. Each gate needs a tiny moment to switch, and that delay adds up along the path. So when the inputs change, the output does not just snap to the answer. It can flicker through wrong values first, a glitch, before it settles. And different paths settle at different times. So here is the problem. If you read the output too early, you read garbage. Nothing on the chip agrees on when the answer is ready. The fix is to give everyone a shared sense of time. We add one special signal, called the clock. It does nothing clever. It just flips between 0 and 1, up and down, at a perfectly steady rate, forever. Think of it as a drummer setting the beat for the whole band. This one wave is sent to every part of the chip, and a fast clock flips 1 billion times every second, or more. Let us name the parts. One full trip, low to high and back to low, is called the period. We write it as capital T. The number of periods packed into 1 second is the frequency. If the period is 1 nanosecond, 1 billionth of a second, then the frequency is 1 gigahertz, 1 billion cycles every second. Frequency is just 1 divided by the period. And notice the two moments where the signal jumps, the rising edge going up and the falling edge coming down. Hold on to that rising edge. Because the rising edge is the moment that matters. Synchronous chips are built to act only on that edge, the instant the clock snaps from 0 to 1. Between edges, the clock holds still and the circuits are free to settle. Then the edge arrives, and every part acts at once, on the same tick. The edge is the shared now that the gates were missing. To use that edge we need a part that can remember. That part is the flip-flop, a tiny 1-bit memory. It has an input we call D, an output we call Q, and a clock input. Here is the rule. The flip-flop ignores its input almost all the time. Only on the rising edge does it look, grab whatever value D has at that instant, and copy it to Q. Then it holds Q rock steady until the next edge. The input can wiggle all it likes in between, and the output does not care. Now put it together. Park a flip-flop, or a row of them called a register, at the start and end of every chunk of logic. On the edge, the first register launches its value. During the period, that value flows through the cloud of gates and settles. On the very next edge, the second register captures the result. Compute, then capture, then repeat. Each tick data marches one stage forward, clean and in step. That steady march is what synchronous logic means. But the edge comes with a strict rule. For a flip-flop to capture cleanly, its input has to be stable for a short window just before the edge, called the setup time, and for a short window just after, called the hold time. Move the data inside that window and the flip-flop is caught mid-decision. Its output can hang between 0 and 1, uncertain, a state called metastability. So the data has to arrive, settle, and sit still before the tick. Stillness near the edge is the whole deal. This is what sets the speed limit. In one clock period, 3 things have to fit. First, the time for the launching flip-flop to push its value out, called clock to Q. Then the delay through all the logic gates. And finally the setup time at the receiving flip-flop. Add them up. The clock period has to be at least that long. So the slowest path through your logic, the critical path, decides everything. Make the logic slower and you must stretch the period, which lowers your maximum frequency. That trade is at the heart of chip speed. One last problem. That edge has to reach millions of flip-flops spread across the whole chip, and ideally reach them all at the same instant. So the clock is not one wire. It is a carefully balanced tree, splitting again and again, often in an H-shaped pattern, so every branch is the same length. When some flip-flops get the edge a little late, that gap is called clock skew, and too much of it breaks the timing we just built. Equal paths keep the whole chip ticking together. So that is the clock, a single steady signal shared by everyone. Its rising edge is the agreed instant to act. Registers sample on that edge and hold. Setup and hold keep the data still around it. The critical path sets how fast you can tick, and the clock tree delivers that tick everywhere at once. One signal, turning a chaos of racing gates into ordered computation.